So I'm going to kick off this explainer with a fact that's probably going to give your old high school physics teacher a literal nervous tick. Ready? Electricity does not run through wires. I mean it. It doesn't travel inside the copper at all. It travels through the void outside of it. So if everything we've been taught feels completely upside down, what exactly is electricity? Let's switch our minds on and figure this whole thing out. Let's just dive right in. Does electricity actually run through wires? It's a pretty provocative question, right? And honestly, it forces a massive paradigm shift. Because think about it. Ever since we were kids, we've pictured wires as these tiny little highways and electricity as, cars just zooming along them. But to really understand the magic of reality, we actually have to completely unlearn that mechanical picture.
To tear down this myth, we've got to look at the classic school book model that we all just kind of blindly accepted. We're taught that in metals, free electrons act like little rebels, breaking off and wandering down the wire. And we naturally assume this physical journey of charged particles just marching forward is exactly what makes up an electric current.
Now, this standard model is usually justified with that famous plumbing analogy, mostly just to keep our brains from overloading. You've probably heard it. It neatly maps voltage to pump pressure, current to the liters of water flowing per second, and resistance to, squeezing the hose. Honestly, it explains Ohm's law in a way that makes perfect intuitive sense. It just clicks. But here is the number that completely ruins that entire textbook picture. 0.1 millimeters per second. Yep, that is the actual drift speed of an electron inside a copper wire. It is shockingly slow. We're talking wading through the metal like thick molasses. Actually, scratch that. It's more like a snail in a coma. At that speed, for an electron to physically travel from your wall switch to your ceiling light bulb, the trip would literally take several hours. And that brings us to a massive, glaring contradiction. If electrons take hours to physically travel from the switch up to the light bulb, why does the room light up the absolute millisecond you flick the switch, right? You push the button and boom, instant light. Did those electrons suddenly, break the speed limit and accelerate to the speed of light? No way. Forget about it. They're still barely crawling along at a fraction of a millimeter per second. So what's the trick here? If the physical particles aren't actually rushing into the bulb to deliver the energy, how on earth does the energy get there so fast? Here is the crucial trick, and it's a real game changer. The electrical energy doesn't travel inside the wire at all. The energy is actually carried by an electromagnetic field that travels in the void, completely on the outside of the wire. Those little electrons crawling inside the metal, they're merely guiding that field. The actual energy is a wave moving through the air around the copper, traveling at the literal speed of light. And you know what's wild? The scientific community has known this since the 19th century. Yet, for some strange reason, our textbooks still insist on drawing those little rebel electrons physically running marathons inside the wire just to power our homes. To visualize this, just imagine a long tube completely packed with rigid balls. If you push one extra ball into the left end, almost instantly, a ball pops out the right end. The ball you pushed didn't sprint all the way through the tube, right? A wave of pressure did. The electrical field works the exact same way. It acts as a pressure wave flying at the speed of light outside the wire, while the individual electrons inside barely move an inch. So it feels pretty great to finally understand how a simple light switch actually works. But does our ability to harness it mean we have electricity totally figured out? Not even close. We're about to cross the frontier into modern physics, where some massive, glaring mysteries about electricity leave the absolute brightest minds totally stumped. The first mystery is arguably the most dramatic, the lightning trigger. Just between us, scientists have a real problem with thunderstorms. We all know the basics, right? Clouds rub together, friction happens, and they accumulate a massive electrical charge. But here is the secret. If you actually measure the voltage inside those storm clouds, it is dozens of times too low to physically break through the resistance of the air and cause a lightning strike to jump to the ground. By literally all the laws of physics we have, lightning just shouldn't be able to spark from those clouds. And yet, as we all know, lightning strikes the Earth millions of times a day. So what exactly acts as the trigger? Well, some physicists guess it might be high-energy cosmic particles shooting in from deep space to carve a conductive path. Others propose these mysterious invisible phenomena called fast positive leaders. But honestly, despite all our advanced sensors, the exact mechanism, the actual trigger that unleashes that hellish discharge from the sky, remains entirely unknown. That brings us to our second massive mystery, high-temperature superconductivity. I know, it sounds like science fiction, but it is very real. Scientists have discovered specific materials that can transmit electrical current with absolutely zero energy loss, literally zero resistance. The current just flows perfectly forever without losing a single drop of energy to heat. It's an absolute miracle of physics that could theoretically revolutionize the entire planet's power grid. But of course, here is the catch. Minus 196 degrees Celsius, we can only achieve this zero resistance miracle when we freeze these ceramic materials in liquid nitrogen. But the real mystery isn't even just the extreme cold, it's the math. For 40 years, physicists have been trying to write the equations to explain exactly why these superconductors work, and the math is still missing. We are actively using a miraculous phenomenon in laboratories all around the world that we literally cannot describe or explain on paper. Crazy, right? And that brings us to the third, and perhaps the deepest, most philosophical mystery of the whole shebang: the fundamental nature of charge itself. We know exactly how charge behaves. We know it comes in positive and negative flavors. We know it's quantized, meaning it comes in distinct, exact little packets. But why does it exist? Why does the universe have this property called charge embedded into particles in the first place? Where did it come from? We have absolutely no idea. We just accept this fundamental property of matter as if it were straight-up magic. Which brings us to our final thoughts. The next time you walk into your kitchen and turn on the kettle to boil some water, I want you to look at the cord. You aren't just pushing little electrons down a copper pipe. You are literally taming an invisible electromagnetic vortex that is flying through the void of space at the speed of light, all just to make a bunch of comatose electrons wiggle slightly inside a metal coil. Reality is so much stranger and honestly so much more fascinating than the textbooks pretend it is. And while we make our tea, the greatest scientists in the world are still staring out the window at a thunderstorm, scratching their heads, wondering how it all actually works. If this explainer completely shifted how you see the world, make sure you stick around for more deep dives into the unbelievable truths hiding in plain sight. So, what everyday magic are you going to question next?